So we'll start a new chapter, that is the module 5, that is electrical system now. So as you are seeing in this picture now, so this is a typical layout of I want to say a power supply system now. So when we are talking about power system, it consists of three things now. One is the generation, then transmission and distribution is there now. So in generation, you're generating the electricity. Either it will be one form of energy to the another form of energy. Either the hydro energy is converted into electrical energy, or the when we are burning a combustion of coal, no, so the steam is produced that we are converting into electrical energy. So what I'm saying, generation system. So there are generators also. They are having transformers also. No? So generation, we are converting one form of energy to the another form of energy by direct conversion. What I would say, hydro is converted into uh, electrical energy or any sort of other energy. No? So generator, main principle of the generator. What is generator? Generator, it's a device which converts the mechanical energy into electrical energy. So when we are talking about this one hydro, no, so it is due to the what do you say, potential energy, no, mgh. So the three parameters comes into play. That is the height, from where the water is coming, and mass and gravity. Now, what is mass? Mass is the matter contained in the body is called mass, right? So we are talking about the generation. So there we are generating the electrical power, and we are generating the power 11 kV or 33 kV. We are generating over there, and there itself they are having the power transformers now. So power transformer, it raise the voltage. So it's a step up transformer, no? So it raised the voltage, and that 11 or 33 kV, and they are raising it and give the voltage that is 132 kV, like that. So that voltage which we are stepping up, we are sending it to the transmission lines now. So bulk power we are sending to the transmission lines. So in transmission lines, okay, the towers are there. Okay, then we have insulators or conductors there. We are having a lot of components over there, like relays, okay, circuit breakers and all that. Now function of relay, it will just whenever the fault occurs in a transmission line, so it will just detect the fault, and it will send a fault, and it will send the signal to the circuit breaker, and the circuit breaker is tripping off. No, so a lot of components are there. That is when we are talking about uh, this one transmission. So as the figure shows now, so generation, either it will be fuel combustion is there, then the power plant, and they are showing the transmission now. So power plant, from their power plant, the electricity to the transmission line, it is going to the substations. Substation from this one, it is going to the transmission lines, and it will go to the other substation also, where the other that is power transformers are installed now. So there, what do I say? It's stepping down the voltage with the help of step down transformers, and then it goes to the industry or our premises. So that voltage, that is 220 volt, or 440 volt, that will go to what am I say, this industry and our premises, right? So in this figure, we have already talked about transmission distribution network, okay, and whatever the electricity is from step down transformer towards the substation, and from there the substation, where from there it is going to what I'm say, industry or our premises. So this one is a pictorial view of this one electric power supply system, right? So now the other thing which we are talking about, so this, that is the power generation now, right? So power generation, when we are talking about power generation plant because fossil fuels are there. And what is fossil fuel? It is nothing but it's a coal, or it will be oil or natural gas or nuclear energy, right? So these are the fall, and whenever the water is falling from top, no, so that is hydel. This one hydro. This one the water is converted into electrical energy. So these are the fossil fuels which we are talking about. That is coal, oil, natural gas, and nuclear energy. And these are the fuels which are the main generating sources in the power plant. Okay, so about 70% other, if you're talking about unconventional generation technologies. Okay, so in that we are talking about cogeneration. We're talking about solar energy, wind generators, and waste materials. Okay, so 70% of the generating capacity that is from the coal, and it is a based coal based thermal plants. No? So here the figure, this one uh, shows that producing a power plant power from coal, no? How the power is coming from coal. So here we have seen the coal supply now. So that coal supply is coming from Jharkhand and all that. So that coal, major sources now, that coal that is there in India, but sooner or later, in some decades now, it will be what I must say, diminished now. So we have to move to other sources, that solar energy and all that. So here we are talking about the principle of thermal power generation. As it is shown that coal supply is there, then conveyor, boiler is there, then steam turbine, generator, condensers, substation, transformer, water purification. When we are talking about, so these are the things which we are going to talk. So here the coal is converted into electricity in thermal power plant, and that coal that it is pulverized. Pulverized means it's in a powder shape, right? It is pulverized. Then that pulverized coal or the powder coal, it will be blown into the water wall boiler. So where it is burnt, and it is burned at a very high temperature, higher than 1300 degrees Celsius or centigrade, and the whatever the heat which are generating in the combustion chamber is transferred into steam, and that high pressure steam is used to run the turbine, steam turbine, and it will spin it. Finally, when the turbine rotates, so it will just the generator to produce uh, electricity. Finally, the turbine rotates, and generator is there to produce the electricity. So what we are saying here, coal, it is converted into electricity in the thermal power plant. It is pulverized. Then the powder coal is blown into the water wall boiler, where it is burned at a higher temperature, more than 1300 degrees Celsius. Then the heat in the combustion gas, it will be transferred to steam, and the high pressure steam is used to run the steam turbine to spin. Finally, the turbine rotates, and the generator uh, to produce electricity. And then one term is the heat rate is there. So what we are talking about in India, the overall efficiency, it is 28% to 30%, um, and it will depend upon the size and the capacity of utilization and the operational practices. And fuel which are there, it's a source of generation, and the common term we are talking about, that is the main thing, that is the heat rate. Okay, then a heat rate, it reflects the efficiency of generation. So what heat rate is, the heat input, whatever the heat input that will be in calories or kilojoules. Okay, so 1 kilowatt hour of electrical output, or a 1 kilowatt hour for electrical energy equivalent to 860 kilocalories of thermal energy, or it will be 3600 kilojoules of thermal energy. So basically, we are talking about heat rate, and it will reflect the efficiency. right? Then the lines are there when we are talking about an electrical system or the power system. So transmission and distribution lines are there. So here in the figure it is showing the tower. No, it's aluminum. This one cross. This one no danger. They are putting over there, and from there upper we are seeing it's a insulated pin type. It will be a suspension type or strain type now. So insulator which are there and the transmission lines it is shown over here. So when you're talking about the frequency, frequency is the number of cycles completed in 1 second. So frequency we are using here that is 50 hertz. Okay, and with a voltage between 11 to 33 kV. Okay, that will be at the power plant site. So the three-phase voltage, whatever the three-phase voltage, we are stepping up and for a higher voltage we are stepping out for transmission uh, on cables that is strung on the cross country towers. They are we are transferring the bulk power from one end to the another end. So then we talked about we are going to talk about the high voltage and extra high voltage now. So, in transmission lines, we are saying that from the generation, it is stepping up by stepping up transformer, that the voltage we are stepping up and sending to the transmission system. So, high voltage, extra high voltage, that will be the next stage from the power plant transfer. Power plant, it will transfer the AC power for long distances, like 220 kV or 400 kV when the transmission is over 1,000 kilometer, and high voltage direct current transmission is there we are using, and it will just minimize the losses. So now the substation network at 132 kV, 110 kV, 66 kV, or 33 kV. So it is the next link towards the end user. Distribution, we are stepping down, that will be 11 kV, 66.6 kV, or 3.3 kV. So it will just last link to the consumer, because in the distribution system, we are stepping down the voltage at the substation, and we are giving the voltage to the industry for 440 volt, and to our premises, our homes, or the consumers, that will be 220. So these are the things of transmission, and then when we talk about the difference between transmission line and distribution line, there is no such difference, but the difference is the line, this one, the voltage level in the line and the power handling capacity. So transmission line, it's obviously it is capable of a large quantity of electric power, and that will for great distances, and they operate at very high voltage. And distribution lines, they are limited, low voltage over there. No? So they are limited quantities of power over shorter distances. Okay. Then losses also are also occurring over there. Power loss is there in the transmission line. So it is proportional to resistance and square of the current. That is P loss equal to I square R. So whenever the higher voltage transmission or distribution, so it will minimize the line drop in the ratio of the voltage. Okay, so that is power loss I square R, right? So if we are taking an instance now, if a distribution of power is raised from 11 kV to 33 kV, then the voltage drop it will lower down by a factor 1 by 3, and I square R, that is the power losses, it will low by a factor, that is 1 by raised to power 2, or square, that will be 1 by 9. So we conclude here that the lower voltage transmission and distribution, it will take the bigger size conductor, and for handling the current capacity. So that is the thing which we are talking about the system over here. Then we are talking about the cascade efficiency now. So cascade efficiency. So when we are talking about the transmission line and this one uh, uh, other distribution, so whatever the primary function of the transmission and whatever the equipments which are installed, yeah, the main function is to transfer the power. That will be a economical way, and it will be reliable from one location to the another. So obviously, conductors they are in this one transmission this line and conductors. It is what I say. It will be copper, it will be aluminum or ASCR, aluminum, steel, real uh, ASCR, aluminum, steel, reinforced. Or when we are talking about their conductors, are just they are it's a form of wires or cable they are swinging on towers, and they poles they are carrying a high voltage AC current. No? Then we have the capacitor also because to improve the power factor, we are installing a capacitor. We talked about in series compensation also. We are having a capacitor. It is they are in series with the transmission line. So capacitors are there. Then circuit interpreter devices is there. That is switches, relays, circuit breaker, fuses. Okay, so isolate now from isolate the system. So we talked about the switches or relays whenever there is a uh, fault in the transmission line. So relay it will just sense the signal and will give the signals. The circuit breaker and circuit breaker is tripping off, right? So when we are talking about the cascade, this one, if we are talking, so the power source to the end energy efficiency link that will be the main factor. And if we'll consider the electricity flow from the generation to the cascade energy efficiency, so typical cascade profile from the generation, that is 11 kV to 33 kV, which are using there in industry. So it is there. So as this figure shows, that is the generation efficiency. That is efficiency beta one. That is the here the efficiency range is there because coal we are talking about 28% to 30 with, and it will depend upon the size of the plant, age of plant or the capacity installation. Then the generation efficiency, then the step up station that is there, and we are stepping up to 400 to 800 kV to enable EHV, extra high voltage transmission. So the maximum loss is 0.5% or the efficiency here 99.5%. Then extra high voltage transmission and station. So extra high voltage transmission substation 400 kV to 800 kV. Here the minimum losses that is 1% and the efficiency of 99%. Then high voltage transmission and station. So high voltage transmission and substation 220 or 400 kV, and it is maximum losses at 2.5% and the efficiency 97.5%. Then substation, sub-transmission, there is sub-transmission either 66 or 132 kV and the minimum loss is 4% and the efficiency of 96%. Then distribution station, so stepping down to level 11 to 33 kV. So the loss is 0.5% or the efficiency 99.5%. Then primary distribution 11 kV to 33 kV with the loss maximum 5% of efficiency of 95%. Then it will come to the end user president. So when we're cascading all the things now, whatever the efficiencies we got here, we have to multiply now. So cascade efficient from generator to the end user, that will be whatever we are getting here. That is 99.5%, then 99%, 97.5%, 96%, 99.5%, 95%. So these all we are multiplying. What are the efficiency in percentage? So whatever the cascade efficiency in the transmission and distribution system, that is from the output of the power plant to the end use, is by calculating it comes at 87%, right? So then the industrial end use, that is premises, again the plant network element, the transformers, receiving substations, switch gears, lines, cables, load circuit breaker, capacitors. So these are there that affect the input received energy. So whatever the losses in the system are major, and it is avoidable, unavoidable. So here single line diagram of the electrical distribution system is shown. This one, the electrical uh, distribution system single line diagram. So here metering, then Projector meter is there. Then we have a transformer that is shown here, right? So these are the for more metering, and from transformer we are saying then it will be substation. So whatever the loss is 1 to 6%, we are putting capacitors over there, feeder capacitor, distribution panel, motors are there. So this is the this one single line diagram for the electrical distribution system. Okay, so one unit saved or two units saved. So whatever the standard technical losses is 70%, 17% in India. Whatever the efficiency, it is 83%, and all these constitute technical losses will be there. Unmetered pilferage, and we are taking out for in this loss, right? So the energy efficiency of the transformer is generally very high. Next, it will go to motor, as shown in this, right? So here, um, a distribution network efficiency that will be including transformer, it is there 95%. So the overall efficiency becomes 50%, that is 0.83 into 9.95. That will be zero point 0.5, and we are taking about this one 50%. So hence one unit saved in end user, it is equivalent to two units generated in the power plant. That is one unit by zero point 0.5 efficiency, that will be two units now. So then we have this electricity billing. So billing we will talk about in the next class. Uh, Here an overview of billing is shown, this one. So we will discuss it in the next class about the billing electricity billing of billing, how it is there. So we'll do it in the next class. Okay, thank you very much.